Our next topic is quantum, why we need it, how it works, and what we need to do to make it go. Our speaker is Dr. Peter Fisher, the Thomas A. Frank Professor of Physics at MIT, who was appointed Associate Provost and Associate VP for Research in October 2022. He also serves as the head of MIT's newly established Office of Research, Computing, and Data. Please join me in welcoming Dr. Peter Fisher.
Oh, wow. Okay. Okay, I want to tell you about quantum mechanics, and I'm a professor, so I'm going to approximate away just about everything. And what I want to leave you with at the end is that quantum mechanics is a global endeavor and a global problem, always has been, always will be. I want to start with three slides about why we need quantum information science. In 3 slides, I want to tell you actually how it works. I want to go right to the bottom and explain to you how a qubit works, why it works the way it does, and how it leads to our optimism that this is really going to make a transformational difference, that it has already started and that will continue. And then what we do to realize that endeavor as a globe. Okay. Oops. All right, 2 reasons we need quantum, big and small. First, small. This is a wafer with integrated circuits on it. It's a highly developed, you can see by its size, it's a 12-inch wafer, pretty modern. And the feature size of the circuits on that wafer are now approaching the width of a few atoms. And you've heard before, you can't go much smaller because you can't make something that's smaller than an atom. It just, atoms have a finite size, it just doesn't work. However, these guys are pretty smart, and they're developing FinFETs, which are field effect transistors, which is the fundamental building block of electronic circuits, that extend into the 3rd dimension. So Moore's law, the 18-month doubling time of computing power, isn't dead. It probably has a couple of decades left in it, and a few factors of 10. But now is a good time, which we're doing, to think about how we're going to compute differently to get away from Moore's law, because somewhere out there in the mists is a fundamental physics limit to the size, the smallness of computing elements that we could build. Oh, you have to push hard. At the other end is large. This is the largest data center in the world, Inner Mongolia Information Park. It's in Inner Mongolia because electricity there costs 3 cents a kilowatt hour, powered by coal. This contains a billion, or quintillion, as we learned yesterday, bytes of data. And that's what's called the exascale. Exa is 10 to the 18th power, or 1 with 18 zeros. This is about the largest data center that you can build. Why? Because in addition to the computers that are inside, there need to be wires carrying current and pipes carrying water to cool them. And as you make it bigger and bigger in 2 dimensions, the fraction of computers to wires and pipes gets small, and you can't build infinitely large, otherwise you just wind up with a big building full of currents and pipes. Again, there is the 3rd dimension. You can go up, so people are starting to talk about multi-level data centers. SpaceX is apparently talking about a spherical data center in space, which would get us another couple of orders of magnitude. But again, this isn't next week's problem, it's not next month's problem, but it's a couple of decades problem, and maybe you can make them a factor of 10 or a factor of 100 bigger. I'm a physicist, thinking kind of round numbers. But someday, we're going to run into a fundamental limit where we can't make computers smaller, we can't make data centers bigger, and we're going to have a finite amount of computing in the world. That's not great, because our demand for computing is growing exponentially. You've heard all the problems that quantum computing has to address, and I think those are the tip of the iceberg, because as we solve those problems, we're going to find more and more bigger and more exciting problems to solve. Okay, we need unbounded computing. Quantum doesn't offer that, but it will offer, we think, several orders of magnitude. Why do we think this? Well, quantum mechanics. And here I'm going to start by talking about the humble bit. So I brought a 6-bit classical memory. Okay, it's an egg carton. Inside, there are these little places. I have a ball. So I can store a 0 or a 1 by where I put the ball, right? And then I can make some mechanical system that performs an operation on the ball and maybe moves it, maybe doesn't move it, but that's computing. And I have to make these little wells deep enough so that if there's some vibration or thermal noise around, the ball stays where it's supposed to stay, as you can see. But that's the physical realization of the bit, which is the basic element of computing today. And I've shown it here on the left. The white curve is just a conceptual or abstraction of this physical object. And this is an important thing in both computing and quantum computing, is the idea of abstraction, that you define a bit conceptually as a place with two minima, and you can put an object in one or the other minima to store data. Another physical realization is a bit, a binary digit, in the form of a relay. And there are electronic versions. You can store a bit in a transistor and a capacitor, but typically, for reasons of error correction, which we'll come to later, you need order a dozen transistors to store a bit. Here is the moment that quantum happens. When we talk about a very small potential well with two places where you can put something, an atomic size object, and a single particle, a single electron, we can begin to see that quantum mechanics doesn't work like classical mechanics, and the object does not sit in one or the other. It sits in both with a probability that we can adjust. So it takes two numbers to describe the relative probability between those two wells. A bit stores one bit of information, a 1 or a 0. A qubit actually stores two real numbers. That's what quantum brings. Two real numbers is an enormous amount of information for such a simple object. That's the conceptual or abstraction. It has physical instantiations. You've heard about storing qubits as photons, qubits as nuclear spins, qubits as electronic circuits. I've shown one here, that's a transmon. But the main thing is that they all look like that mathematically. A potential well with two places where you can put something and a probability. That's what quantum mechanics brings. You no longer talk about it's here or there, it's in both places. And it's in both places in a way that you can set up. All right. If you bring two qubits into close proximity and allow them to talk to each other, again, by some means I don't have to specify, but is physically possible. I've shown this here, qubit 1, qubit 2. There are 4 combinations of things that happen. So the left well can talk from qubit 1 to the left well in qubit 2, or to the right well in qubit 2, and so on. So there are 4 combinations. And the thing that happens, and to me this is one of the most fascinating things about this whole story, is that these 2 qubits conceptually are no longer separate objects, they're one object, and that's called entanglement. And so you talk about them mathematically in the way shown on the right, where there are 4 potential wells, and again, encoded are probabilities of a particle being in each one of the wells that encode 4 real numbers. So by adding a qubit, you've doubled the number of quantities that you can store. That's what this whole field is really about. Quantum sensors actually, interestingly, work by moving the little minima around in a way that alters the probabilities that a particle is there or not, so that when you measure, you can detect very small motions. So this picture is really the underlying picture of everything in quantum information science. Okay, so this should convince you that if I bring up a 3rd qubit and connect it or entangle it with the other 2, then I'd have 8. And 1 more is 16. And so I can just count up number of qubits versus number of stored quantities. 10 qubits is about 1,000 stored quantities. So if I get to 60, I have 1 with 18 digits after it, close to 1 times 10 to the 18th. That's the exascale. And you heard yesterday that 60 qubits gets you to the exascale. And so that system of 60 qubits is going to have the same storage capacity and processing possibility as that huge data center I showed you in the third slide. This is the hope. There is lots and lots of things that need to happen for us to realize that hope. So I'm going to talk about a few of the challenges. One of the most interesting things about a classical storage system like this, remember I shook it, at finite temperature everything is shaking. And so in the previous talk you heard about the need to cool quantum systems to prevent the shaking. That's what this is all about. You have to do the same thing with classical systems, just not as much, because what you don't want to have happen is for the thermal noise to cause the bit to flip. Error correcting code can take care of that. But basically, anytime you move the marker from one well to the other, coming down the other side, some energy has to be radiated. That will be important later on. So a challenge in the 1970s, as integrated circuits got denser and denser, was exactly the same thing we're facing now, quantum mechanically, is error correction. Entanglement, which I just described, is even more delicate. And it's not just thermal noise, it's electrical noise, and it's noise that we don't even understand at this point. And so a real physical qubit, a real abstract qubit, might need tens, hundreds, or thousands of conceptual physical qubits to store that 1 qubit of information. And that's what quantum error correction is all about. It's reducing this noise and making reliable qubit storage. So you can just think of it as a 2-well potential and not as, a bazillion transistors. The second thing relates to the first, which is energy. When I flip this bit, whether I do it electrically or with my hand, when the marker comes down on the other side, it drops and dissipates some energy. So every calculation you do releases some energy. Freeman Dyson, who is a visionary physicist, was able to calculate the potential of human thought just by measuring the power generated in the human brain and dividing by the temperature, and that gives you the maximum possible number of bit flips that the human can do. It's pretty hard and we're not very efficient. But this is what leads that data center that I showed you to require 100 megawatts, is these bits flipping. Similarly, we heard a couple of talks ago in the plenary session this morning that the actual quantum computer sits down here and is a very, very small chip. And all of this, which is called the balance of the system, supports the operation of that chip by providing very low temperature and control signals that set the quantum system up and then read the quantum system out. So how all of this plays in to the energy balance of the system is critical. Remember, the data center I showed you, and there are order 8,000 data centers in the world, consumed 100 megawatts. We can't go on like that much more from a sustainability point of view. And the bit flipping down here doesn't take much energy quantum mechanically, but the concern is the energy efficiency of this entire system. Okay, so my last slide is all of this is a global effort. No one group, even our folks at MIT, are going to solve this problem. The quantum error correction has had a lot of good ideas, some progress, but is by no means a solved problem. The qubit technology is still evolving. No clear winner yet. Good luck to all of you. Quantum algorithms are in their infancy, but developing quickly. But the main thing for this group is the supporting technology. All of the things that are going to be needed that are outside of, my conceptual little egg holder or the little chip at the bottom of that big chandelier, that's going to be 99% of the work, and I thank you all for doing it. I'll close by telling you quantum theory is still advancing. Quantum mechanics is not a completely understood theory. It is the theory of the universe. It is one of the two theories that we have that we believe is exact, meaning no exceptions to the rules of quantum mechanics, no exceptions to the rules of gravity. The problem is we don't know how quantum mechanics and gravity work together. This is a black hole. This is an actual picture of a black hole that was taken with a radio telescope, a system of radio telescopes a few years ago. And a colleague of mine, Daniel Harlow, has shown that that black hole encodes information on its surface using 3-bit quantum error correction, which is quite remarkable. So thank you for your attention, and thank you mainly for your work in this really important field, and good luck.